Right then, guys, we are now going to go through this paper, as I promised. Now, we started this in the lesson. We will talk about all of it. So, first of all, we had this one. We had to write the number here. We appreciated this was the number 2. I know we did this in the lesson. We're going to talk about it anyway. So, what would you see in this reaction? Now, for this, we've got to look at the state symbols here. So, we've got a solid, we've got an aqueous. Over here, we've got an aqueous and a liquid. Now, a lot of you wrote bubbles, fizzing, but where is the gas? If there was going to be bubbles, there'd be gas. There isn't any gas, therefore, that's not the thing. Now, we've got a solid over here and no solid here. So, basically, the solid disappears. Is what you're looking for. Disappears. There you go. Brilliant. Now, let's keep going. Let's keep going to the next bit of the. Okay, double page. Lovely. So we've got our electrolysis equation here. So we've got 4OH minus. Now, we've got 4 minuses here. Therefore, it's going to make 4. That's a terrible 4 electrons. Okay. Now, what can we make from O and H? Now, it says up here it forms oxygen. It's going to form oxygen. Okay. And the other thing we're going to make is, with the H's, is a little bit of water. So, we just then need 2 of those to balance it out. Brilliant. Nice. So, what do we need to do to the copper cathode after it's been removed from the copper sulfate before the final mass is determined? Okay, so you've taken it out. It's a bit wet. Okay, so we need to pat it. Hang on. I've lost my ability to write now. Hold on a second. Here I am trying to be clever and I've lost my ability to write. So, we're going to pat it. Pat it dry. Maybe rinse it, gently. Gently. Because, of course, if you do this too vigorously, you're going to wash your copper off. Okay? And then you're going to put it in the oven. Put it in the oven. That's a good place to dry something. Put it in the oven. That's a good place to dry something. Brilliant. Right. Explain, it says, in terms of ions, the change in mass of the cathode shown in figure 3. Okay, now you've got to essentially say, okay, here the copper ions go to the cathode. They go to the cathode. Now please note, use the term ions. So talk about ions, okay? Now, they gain 2 electrons. Say 2. Say the number of electrons, okay? And what do they form, okay? They form copper atoms. We're going to say atoms. Remember, be really specific with your terms here, guys. That really matters, okay? It really matters being so specific with your terms. Okay, now why it says, does the colour of the copper sulfate not change? We look over here, it remains a pale blue solution. So, essentially, at the cathode, okay, copper ions leave the solution. We know this, we've just said they do. Okay, but at the anode, copper ions enter the solution. So they're taken out of the cathode, but they're put back in at the anode. There's no overall change in concentration. Okay, so basically, ions are taken out, ions are put back in, it stays there, okay, because the concentration of ions has not changed. Okay, next. Ooh, this one, I love this one. Now, this one tripped a lot of people up, okay, look, let's have a read of it. Sodium carbonate has the formula Na2CO3. It contains ions, look, ion. They're saying ion a lot. I think they want you to use the term ion here because they're saying ions so much. That's a bit of a clue. Now, what's the configuration? So it says atomic number of sodium is 11. Feel free, by the way, I said this, guys, jot all over your paper like this. As an examiner, we don't mind. Okay, that means the atom, not ion, has 11 electrons. Okay, but it's asking you about the ion. Now, if it's +1, it means it's lost 1 electron. Okay, so how many electrons does it have? This means it now has 10 electrons, and the electron configuration of that would be 2, 8 left, 8. Okay, so B is the answer. Lots of you put C. Remember, this one is the ion, this one is the atom. These two are just wrong. Okay, now, what's it asking you for? There we go. A lot of people fell over on that. That's why they did it. They did it to make you fall over. And we want to make sure you don't do that in the real thing. Now, next, we have explain why solid sodium carbonate cannot conduct electricity, but a solution of sodium carbonate can conduct electricity. Now, remember, what's the word they've used up here? 1, 2, 3 times. Ions. Okay? Now, you have to talk, these are ionic. See, the ions are the things that do things. If you write electrons, 0. Okay? So, in a solid, I'm not going to waffle. Okay? I'm not going to write loads. Ions are strongly held in a lattice. Think of your solid. That's a terrible drawing of solid, but you get me. They're tightly packed together, aren't they? They're strongly held, so they can't move. Okay, in a liquid, however, they can move. Okay, so I've been incredibly remiss here, and what I haven't done is write ions everywhere. Ions, ions. The ions are strongly held in a lattice, so the ions can't move. In a liquid, the ions can move. Okay, say ions all the time. Keep talking about ions. Look how many times they've said the word ions. They want you to work this out and say ions. Nice. Now, this next one always baffles me. I was talking to Miss Hammond. She's also baffled by it, because when we talk to you in maths, in a maths lesson, you can do percentages so easily. This is like the easiest thing ever. You know, I said to you in class, you know, what are the percentage of girls in this class? You go, oh right, so it's the number of girls divided by the total number of people in the class times 100. That's it. Okay, and this is no different. So, percentage by mass of sodium in sodium carbonate. So, we're looking for the sodium. Now, how many sodiums are there in Na2? There are 2. Okay, there are 2 sodiums. Okay, so you need 1 sodium being 23. You need 2 of those, which is 46. You then need the formula mass of Na2CO3, which we can work out as, in fact, should we work it out? That'll be helpful. So we've got 2 times 23 plus 12 plus 3 times 16. Now again, I keep saying this, you get marks just for doing that. So if you write that equals 106, that is one of the 3 marks right there. If you can't remember how to do these quantitative things, work out the MR. Work out the MR of the things. You're going to get something. Okay? So it's 46 divided by 106 times 100. Okay? And that equals 43.4%. Brilliant. Nice. Halfway through my little sheet I gave you. Now the next one says, oh, this was a tricky one. Okay, because they're 2 different terms. You think they're the same thing, maybe the opposite of each other, but they're not. They're 2 different terms, which threw a lot of people. Now, a dilute solution, think of squash. If you think of squash, how much squash is in a very dilute glass of squash? There's very little bit of squash, and there's a lot of water. Okay, so to make a dilute hydrochloric acid solution, come on, pen. I've moved it. I've tried to be clever, and it's decided now I do not now have the permission to write. Hang on. I can move things, but I can't write. Hang on, I think I right clicked, didn't I? And that made it work. There we go, I'm back. Right, so a dilute solution basically has a lot of water. Okay, so you could say lots of water, but it wants to know about the acid in this term. Okay, so a dilute solution has a low concentration of H plus ions. Okay, now remember, an acid involves H plus ions, hydrogen ions. Okay, because a higher tier, less be using these terms. You could also write, just to cement that you understand, okay, it is a high concentration of water, H2O. It's mostly water, not many H plus ions. Right, now, strong acid, remember, the opposite of dilute is concentrated. It's not strong, okay? Strong and weak. Okay, so we've got a strong acid and a weak acid. You've got a dilute acid and you've got a concentrated acid. You can have a dilute strong acid. You can have a concentrated weak acid. You can have those things, right? So, in a strong acid, it fully dissociates, I'm wandering off the line here, to form H plus ions. That's it. That's the definition of a strong acid. Easy peasy. Right, now, this next one. It says, work out the formula or the number of atoms. So you're going to calculate here. I'm leaning on my little trackpad here. Calculate the number of atoms that combine together to form 16.25 grams of lead ethanoate. Now, lead ethanoate is this bad boy up here. So, what did I say about the maths questions? Let's work out the MR of sodium ethanoate. Let's do that. Now, lead, it tells you here, so easy. 207, okay? Plus, now remember, the 2 outside the brackets, this means there is 2 of everything in the brackets, okay? 2 of everything in the brackets. I shouldn't have done that because I've just written over 16.25, which is very important. Okay, so there's 2 of everything in the brackets. Okay, so what we then need to do is essentially do that. Okay, we then work out what's in the brackets and multiply it by 2. So we're going to go 207 plus 2 times, and then we're going to work out the stuff in the brackets. So it's 2 times 12 plus 3 times 1. Okay, so there's 2 carbons, 3 hydrogens. Okay, plus 2 times 16, because there are 2 oxygens. And all that times by 2, and that gives you 325. Okay, and one of the 4 marks is just for that. So 25% of the marks for this question is just to do that. You might as well do that, have a go at that. That's easy enough, that's straightforward enough. Okay, now, next thing, okay, we're going to work out number of atoms and use Avogadro's number. So we should be thinking moles. I'm going to work out the number of moles now, because you know that this is the number of atoms in 1 mole. Okay, 1 mole of lead ethanoate will have this number of atoms. So the first thing we need to know is how many moles we have in 16.25 grams. So 16.25, remember, I'll write over here, mole is mass divided by MR. So 16.25 divided by 325, okay, and that gives you 0.05. What a beautifully nice number. It's almost as if they made that number to be just like that, just for you. Okay, so we have that number of moles. This is our number of moles here. We have this number of moles. Now, to work out the number of, okay, to work out the number of these, how many of these do we have? Because remember, this is the number of these in 1 mole. Okay, so we've got 0.05 times 6.02 times 10 to the 23. This means 3.01 times 10 to 22. That is how many PbCH3COO2s we have. We have that number of these. But you have to identify, hopefully you can identify, that in these there is 1, and then 2 of everything in here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. There are 15 atoms in this molecule. Okay, so to work out our number of atoms, you just do 15 times 3.01 times 10 to the 22, which gives you a grand total of 4.515 times 10 to the 23. That was a big old question, but it's 4 marks, remember, guys. So, you know, lots of opportunities for you to show your understanding there. Next, iron is more reactive than copper. Now, it's asking you in this one to work out which one of these two equations is true based on some experimental results. Okay, so they're giving you the mass of something, and you want to work out which one is true. Now, remember, you can't compare these masses directly. Okay, 2 grams of iron will contain a different number of atoms to 2 grams of copper. You can't compare those. What can you compare? We've got to turn these into moles. You can then compare those. Okay, so let's go for it. So we've got 2.24 of iron divided by 56. If I plug that in my lovely calculator, I will get 0.04 moles of iron. We have 3.81 grams of copper. Divide that by 63.5. That gives us 0.06 grams moles of copper. Okay, so basically we've now got to turn this, I think, into a ratio. So we could just say, let's just say basically it's 4 to 6, 0.04, 0.06. Let's make life easy for ourselves. 4 to 6, okay? Now, can we simplify that? Of course we can. It's 2 to 3, okay? So the ratio of iron to copper is 2 to 3. Therefore, look at this. Equation 2 is a ratio of 2 iron to 3 copper. Therefore, equation 2 is correct. Now, the annoying thing, which a lot of us got, is you get this 3rd mark with your workings. This is mark 3. If you don't specifically say that bit, okay, you're not going to get the 3rd mark. Okay, you've done all the work. You've just got to identify, because it asks you, show which equation. Show it. If you don't write this bit here, you haven't shown it. Show it. Okay, final 2 pages now. Now, as I said when we started going through these, we are going now down the list of questions people didn't do very well on. Okay, so we're now getting to ones that people actually did okay on. So some of these questions weren't done really badly. Okay, there was a couple of marks missing, and to be honest, I had a blank page. I thought I might as well chuck another pair of questions in rather than leave a blank page for you. So, 2 advantages of obtaining metals by recycling. There are loads of reasons you could use for this. Okay, you could say uses less energy. Okay, less energy required to recycle them than make them from scratch. Okay, doesn't fill landfill. That's another one. Okay, doesn't fill the landfill. If you're recycling the metals, you're not putting them in landfill. Now, you could say other things. You could say less fossil fuels burned to generate the electricity to make the metals in the first place. Loads of reasons for that. That question was done quite well. That bit wasn't part of the bit that was done badly, but it's on the page with something that wasn't done well. So, this one, okay, a lot of you identified what redox was, and we had to explain why it was that. So, of course, redox, which a lot of you identified, is where reduction and oxidation are occurring. Okay, so reduction and oxidation are occurring at the same time. That's a redox reaction. Okay, what we now need to be really careful with is remembering our oil rig. Okay, which means oxidation is loss of electrons and reduction is gain of electrons. So what have we got here? We've got Cd2+ becoming Cd. Okay, now that has gained electrons. A lot of you lost marks because you said it lost. That has gained electrons. Okay, that means it's been reduced. Now the other one, I'll try and squeeze it in. Zn to Zn2+. that has lost electrons and has been oxidized. Okay, now a lot of you lost marks because you put those two things the wrong way around. You said the cadmium had been oxidized and the zinc had been reduced. Okay, so be really careful with that. Okay, now last one here we have our very last question we're going to look at today. We've got our formula of calcium phosphate, cadmium phosphate, sorry, not calcium, cadmium. Now what we're going to do here, just to make our lives really easy, is we're just going to use the crossover method. So we've got Cd2 plus PO4 3 minus. What we know, of course, is we take that number, we put it down there, we take that number, we put it down there, meaning it is going to be CD3PO4 in brackets, otherwise it would be PO42. That's just crazy. PO42. So the answer is quite obviously C. Okay. Now, one of the advantages of biological methods of extracting metals is using bacteria. Give one disadvantage of this method of extracting metals from low-grade ores. All you need to say there, okay, is it's very slow. One of the major disadvantages of phytomining, and in this case bioleaching, is it's very slow. Okay, they're very slow. Just remember, very slow. It's all good. Right, there's final question. Now you could have gone two ways on this. First of all, we're describing. Okay, so you're saying what you would see. Say what you see. Say what you would do. Describe how. How would you do it? Describe how you would do it. Say what you would do. If I said you're going to do this, what would you do? Okay, you wouldn't explain what's going on. You're not going to say, well, you know, it's going to be a displacement reaction and stuff. No, no, no. You're literally just saying what you would do in this experiment. So essentially, you could do two things. Number one is you could add carbon. Okay, it's low in the reactivity series. It's below carbon. Okay, so add carbon and heat. You're going to add carbon, you're going to heat it. You'll remember doing the copper, you had to heat it. You'll remember the match and the iron, you had to heat it. That was the heat. The match burning was the heat. Okay, that's the heat. You add the carbon, you heat. That will give you lead. Okay. Now number two, okay, is you could do electrolysis. But importantly, what you've got to do, okay, is to make sure you get both marks for this, is you're going to react lead oxide with an acid, okay, and do electrolysis on the products. That bit's important, okay, because you can't do electrolysis on lead oxide, okay, because it's a solid. Nice. Okay, so we are going to now finish it up here. Thank you very much for watching. I hope that's helpful. Make sure you fill this in and you understand. Any questions, come see me, give me a shout. I will help. Thank you very much, guys. Goodbye.